So let's think about angle change. So this is the initial configuration we have. And angle can be defined by two vectors, right? Can you define angle with one vector, only one vector? That's not possible. So to define angle, at least we need to have a two vector. So let's say originally we have a two vector. Two vectors normal to each other. And so pi over 2, 90 degree. And first vector is dx, second vector dy. And deformed configuration, both vectors will change its direction and something like that. Its angle is changing. Pi over 2 minus theta, let's say, dx, dy. How can we measure the angle of two vectors? How can we measure the angle of two vectors in the space? We need to use dot product, right? Scalar product. Because, so scalar product, let's say scalar product of two vectors, x and y, is, from its definition, a magnitude of dx, magnitude of dy, and cosine theta. So actually here, 2 pi minus theta, pi over 2 minus theta, right? And this is the same to the dx, dy, sine theta. So angle sine theta equal dx dot dy, and magnitude of vector dx dy. And this equation become, because we know the relation between this vector, lowercase d x vector, and uppercase x vector. Its relation is given by deformation tensor, right? So this become dx transpose f transpose f dy. And how about this? This is a magnitude of lowercase x can be calculated by the length change. So let's say 1 plus lambda x dx 1 plus lambda y dy. This is result from the last lecture. Then sine theta equal dx transpose. Here 2E Green-Lagrange strain tensor. Okay. And cross I dy t and 1 plus lambda x one plus lambda y dx dy. This is the same to the, so finally we have a sine x sine zeta equal okay. So that identity matrix is removed because x t I y equal t y equal dot product y 0, because the x and y vector at initial configuration are normal to each other, 90 degrees. So dot product of these two vectors is 0. So this is the final result. We can calculate the zeta after deformation on current configuration. So okay. So equation looks complicated, but let's try to understand that equation. If dx equal some vector nx, it's a unit vector, and y equal ny, the other unit vector. And let's put this into that equation. Then what happened? Then sine theta equal 1 plus lambda x, 1 plus lambda y. And magnitude of n vector is unit. So this is like this. And 2 n x e Green-Lagrange strain tensor and y. This is our result. And for example, let's put nx equal ex. So E1. Let's put the E1. One direction. And y equal E2. E1 and E2 is a base vector of a Cartesian coordinate system. And both vectors are normal to each other. The angle between both vectors are 90 degrees. So we can put E1, E2. Then sine theta, let's say E1, E2 equal one plus, let's say lambda 1, 1 plus lambda 2, and 2 E1 E, and I need to have transpose E2. And 2E1. What's this? E12. That's a off-diagonal component of a Green-Lagrange strain tensor. So generally, sine theta E alpha E beta equal 2E alpha beta and 1 plus lambda alpha, 1 plus lambda beta. And here alpha beta equal 1, 2, 3, and alpha beta is different. If alpha and beta is the same, we cannot calculate the angle change, right? So this equation means Green-Lagrange strain tensor have a 9 component E11, E22, E33, 1, 2, E13, E23. Actually, this is symmetric. Okay? And this diagonal component have information about length change, right? We discussed on that in the last lecture. And this part, off diagonal part, have information on angle change, right? This is a length change. So E11 mean have a represent length change in x direction, length change in y direction, length change in z direction. E12 angle change between E1 and E2 vector, angle change between E1 and E3 vector, angle change between E2 and E3. So off diagonal term give us angle change between 2 of 3 base vector. Okay, understand? So we can understand the Green-Lagrange strain tensor have information on length change and angle change. That's the most important thing. We need to physically understand the strain. So finite deformation theory. Finite deformation. Finite means deformation don't need to be small. Deformation can be big, right? In your undergraduate solid mechanics or structural mechanics class, one of the most important and basic assumption was that deformation is small, right? So strain is small too. But this finite deformation theory doesn't need that kind of assumption, okay? So this is a much more general theory. And we already have the basics about finite deformation theory. Green-Lagrange strain, angle change, volume change. These are all about finite deformation theory, okay? Now let me think about displacement. So again, we have a Cartesian coordinate system, E1, E2, E3. And we have a initial body. Initial configuration. And current configuration here so I said the bodies are made by a lot of small material points, right? And this is one of that material point. And each position is represented by x, vector x. And during the deformation, this vector moves to another position. And this is a new position, x. And displacement u equal current position minus initial position. This is a u, right? We know this. Displacement is just difference between the position, initial and current position. We know about that. And then between the initial and current, there are relationship of mapping. Okay, I introduced already this. And between the current material vector and initial material vector, the relation is deformation gradient or deformation tensor, 3x3 matrix. And based on this, we calculate a lot of things, right? Volume change, length change, and angle change, and change of surface, right? And so let's consider displacement vector here, this one, and F. This is deformation tensor, can be calculated by like this, dx. And this become and d x plus u. Right? Because of this. Is that right? Okay. Then I plus u dx. So deformation tensor can be given by displacement, right? So here we have displacement here. And let me calculate the Green-Lagrange strain tensor in terms of displacement. Green-Lagrange strain tensor E equal 1 over 2 deformation gradient FTF minus I. Let's put that result into here. 1 over 2 and x plus I transpose minus I. Okay. This become 1 over 2 transpose plus this is finally, sorry, something, I need to put u here, u, not the x, u, 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 u. Okay, so this transpose can be go inside of this bracket. And then we have two term here, two term. So if we multiply this term and this term, we can have four term, right? You can think this is a bracket A plus B, bracket C plus D, something like this. So, and here I multiplied by I is subtract by I. So we have only three terms. Looks like this. So Green-Lagrange strain tensor can be written by displacement u instead of current position x. right? And with the tensor form, component of Green-Lagrange strain Eij equal one over two, okay, duj dxi plus dui dxj plus duj dxk dui dxk. Let me see. Sorry, I did. This should be k. K, K, J, I. Understand? Any question? So usually I think I define all the derivative about the partial. So everything should be partial. Something like that. So partial. But no big difference. Just change, small change. No big difference. So if we don't consider the time, this is fine. But if we consider the time, so it should be a partial. Usually, displacement or position depends on each space and time, right? But here, I didn't consider the time, so this is fine. But if you want, you can change the partial derivative, something like that. Here also partial. Okay. So in general, actually, x equal function of position and time. So, but in our case, we didn't consider the time. Okay. Now let's consider small deformation theory. small deformation. So you are very familiar with small deformation theory, right? Here. Small deformation. In small deformation theory, the assumption, major assumption is its deformation gradient. Magnitude of deformation gradient is much smaller than 1. So, gradient. This is a displacement. X is a initial configuration, right? This value is much small, very, very small. So this means transpose much smaller than 1. Watch this. Watch this. Watch this term. This is a quite special operator. So let's say A, I, watch this. This means A, okay, let me give an operator. This is define the operator. A, B equal A 1 1 B 1 1 plus A 1 2 B 1 2 plus something like that. A and N, B and N. We multiply each corresponding component and sum together. This operator means sum I equal 1 2 3, sum J equal 1 2 3, AI J B I J. So just simply Aij, Bij. And if I use that operator with the identity matrix, then this gives us A11, A22 plus A3. Watch this. This is just summation of the only diagonal component. This is a basic assumption. Okay, with that assumption, let's use the deformation tensor was partial x partial current plus I. And, U. In this equation, become we can write down this term with two terms, this term and this. What's this? Name of this? Chain rule. You know the chain rule. Right? Based on chain rule, we can decompose this equation with two parts. And this become and what's this? This is deformation gradient F. Right? And that term X U X become again X U plus I. And it become plus right? So, let's consider this equation. So, finally we have what we have finally is that partial X, partial U, Y, this one. And let's compare both parts. Finite deformation theory, left side and right side is same. But how about in small deformation theory? Small deformation theory, gradient or displacement is very small. Much smaller than 1. So, this part is very small. Much, much smaller than this one and this one. So, this is small one, and this is a small one multiplied by the other small one. So, this part is much, much smaller than these two. So, finally, we can have X U equal U. In small deformation theory, we can use this relation. Let's say not the same, actually similar. Yeah, this is physically correct. So This is your original configuration. Okay? And small deformation theory, there are very, very small deformation here. This is current configuration. So, regarding the geometry, current and initial geometry is very similar. No big difference. So, even we are taking the derivative, gradient about initial configuration and current configuration. Both are similar. So, almost same. So, here the gradient of displacement u about the initial configuration, initial geometry, can be replaced by the gradient of displacement about current geometry. Okay? Because the x and x is similar. And u is much, much smaller than 1. So when we derived some equation and finally got some result, we need to try to understand what's the physical meaning of that equation. That's very important, okay? And let's go back to the let's go back to this one. Gradient. So gradient, deformation gradient was by its definition x u plus I, and in small deformation theory it's similar to the x u plus I. So only change is that here, okay, uppercase x changed to the lowercase x. And okay, in tensor, ui plus ij partial xj ui j. Okay. Any question? So now we know what happened, what changed in small deformation theory against finite deformation theory. And let's consider volume change. So volume change. Volume change was in finite deformation theory, deformation determinant f d omega 0. This was the original equation in finite deformation theory, and it's similar to the determinant O u plus I d omega 0. Right? And okay, it's the same. Determinant of plus 1 right? In matrix form, this one plus I looks like that. We can calculate the determinants of this matrix. Then that equation, if we calculate determinant 1 plus x1, u1, x2, u2, x3, u3 plus quadratic term. d omega. Quadratic term means the square term. Okay? And because this quadratic term is much smaller than this linear term, right? So finally, we can find the volume change equal 1 plus partial xi partial ui d omega 0. So we can have only these three, or 1 plus divergence u d omega 0. You know divergence, right? Divergence something equal dot product u and transpose nabla. So in small deformation theory, the volume change can be very easily calculated by only these three components. That's the very well known, right? In fluid mechanics and solid mechanics.